Okay, welcome back. What I want to do is to look at Tittingill's Electrotechnical Technology Level 3. Now again, what I want to look at is DC machines. Okay, now you've seen that I've done quite a number of videos on machines because it plays a very high level and a very important part in being an electrician. Okay, now what that means is that it allows you to work in commercial, industrial, or domestic premises, and it provides you with a lot more knowledge that makes you equipped to deal with any motors in a given situation. Okay, so you need to read the information, take it down, and make it your own. Don't just think you can read it off the screen. That's not going to work too good. Okay, right. Again, these machines. Okay, now here, all I'm going to want to look at is the outcome. Okay, understand the functions of electrical machines. Now, at the end of this session, you should be able to, or at the end of this session, the students should be able to describe the principal operation of the DC machine and the production of a rotating magnetic field from a three-phase supply. Okay. Now here, an electrical machine acts to convert mechanical energy to electrical energy when it is a generator or electrical to mechanical energy as a motor. Now, electrical machines always involve the interaction between two magnetic fields. Okay. Now let me just go in and take these fields as individually, and here you'll see that in this case here the magnetic fields are repulsed, okay, because like poles repel. So these are your magnetic fields repulsing each other. Okay. Now here you have magnetic north and south, and these two poles will attract. Okay. Let's just make sure we get the opposite poles attract, like poles repel. Okay. Now, as for this type of magnetic field, this is the kind of field you will have around an inductor. Okay, in regards to that. Now, it doesn't matter whether it's just 2 volts or whatever, a magnetic field will exist. Okay, let's just go down a bit, make sure we can get this in full view. Okay. Now here, when a conductor has a current flowing through it, a magnetic field is created around the conductor. The strength of the magnetic field can be increased by increasing the number of conductors or increasing the current flowing in the conductors. Now, if I want to strengthen my magnetic field, I can increase the coils, the number of coils. So rather than just put on 4 coils, for instance, I can make that coil 8 coils. I can make it 12, 16 coils. Therefore, that will strengthen my magnetic field. Or I can leave it as 4 coils but increase the current in the coil. The problem with increasing the current in the coil is that if it's a given size conductor, let's say for argument's sake it was just a 1.5 millimeter conductor, and I increase the current, then I could well be taking that conductor to exceed its current handling capacity. So that I would have to take into account. Okay, so be aware of that. Okay, let's go up, make sure we bring everything back into view. Okay. Okay. Now, bear in mind that when this says A code, it means that there is no magnetic core in this conductor, in this cylinder, I should say. Okay. But if you were to put a iron core into that cylinder, you would increase the magnetic field some tenfold, if not more. Okay. Basic DC machine. Now, here you have, again, this is your yoke. Okay. Armature windings. Okay. These are your poles. Okay. So you have 4 poles, 2 pairs. Okay. Now this you should be able to read for yourself. So I don't really want to begin to go into reading this out to you, because you're not kids now. You're big guys now, and big ladies as well. When I say big ladies, I mean as an adult form, not in any other reference. Okay, so purely let's just clarify that, ladies and gentlemen, whether irrespective of who you are. Okay, no offense intended to anyone, please note. Now the outer casing is made from cast iron or a similar material that is easily magnetized, and is called yoke. The motor shown has 4 pole cores made of laminated steel which are bolted to the yoke. This allows for an increase in the area of the magnetic path and distributes the magnetic flux evenly around the armature. Some DC machines have compoles or interpoles that are set between the main poles. These reduce the sparking that occurs at the brushes. Okay, make sure bring this more so into so you can see it in full. Okay, hopefully pan out. Okay, make sure we get everything in view. Okay, and here is your interpoles. Okay, now if you look at the difference, let me just go back. Okay, if you look at this here, you'll see that here there are no interpoles on this motor here. Okay, okay, it's just showing you the main poles and yoke. But then as we go forward, we can now see the interpoles here, 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 and here. Okay, and those interpoles reduce the spark arcing when the brushes makes contact. Okay. Okay. Let's pan out a bit. Okay. Now the field windings are coils wrapped around the pole cores and provide one of the magnetic fields. Current flows in the windings, creating a magnetic circuit within the yoke and the pole cores. This magnetic circuit provides a series of north and south poles. Okay. Okay, just want to make sure that it can be seen. Okay. Okay. And here you have just the armature. The central part of the machine is called the armature. The armature has slots running down its length, which have a series of windings called armature windings. Now here is where the motor will sit. The armature will sit in on bearings, and it is central in the stator or yoke structure, if you wish. Okay. Now the armature windings start and finish at the point on the armature called the commutator. They are housed in a laminated soft iron core. Okay. Okay. And here is your brushes, okay, and that's your commutator, okay. That would be a fan which rotates at the same time to provide cooling, okay. Now here you can read this for yourself. You don't need me to read this to you, okay. Let me just pan out, make sure we can get it all in, okay. And now pan back, okay. Okay. Okay, good. Now commutation or commutator. Okay. Now if you look at this carefully, you will see how the commutator is made up. Okay, purely made up in segments. And again here, just going to make sure that we can give you a view of it. Okay. 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 Okay, carbon brushes are set so that one of them acts as the positive of the DC and the other acts as the negative. This is also what the commutator does. As the armature rotates in the magnetic field, an induced EMF is created within the armature winding. This induced EMF creates an induced current. This induced EMF appears at the commutator, but because the armature is rotating, it produces an alternating EMF. Okay? And EMF stands for electromotive force. I repeat, EMF stands for electromotive force. Okay? Okay. And here's how it's showing you now how the commutator is made up in segments, okay? And I hope this comes out clearer than it looks on my camera. Okay. A commutator is made up of a series of segments which are conductors separated by thin pieces of insulator such as mica. Mica is basically compressed paper, okay? Again, here you can read this for yourself. You don't need me to be reading this out to you. If the machine were a generator, the armature would be driven by an external mechanical source, and a DC supply would be supplied to the field coil. This is called the excitation current. Okay? The carbon brushes are set so that one of them acts as the positive of the DC, as previously mentioned, whilst the other acts as the negative, as previously mentioned. This is also the function of the commutator. Okay. And here we have a clearer picture, okay, showing you the more precise segments of your commutator and how it is made up and wired. Now this is for you to draw out, basically, to extract the information and make it your own. So don't ignore it, okay? Okay, right. Okay, thank you, good. And here is your waveforms, okay? This is your natural DC waveform, okay? And this is what you will call your a ripple AC. But when we take this now becomes this when we put it through a capacitor, and the capacitor reduces the amount of ripple. So we're looking for something that becomes a smooth DC. So even more capacitor rectification than this. So we have almost a straight line DC, okay? And that's what we will be looking for. Yeah. Reduce AC ripple, and that is reduced by using a capacitor. We can reduce it, make it smaller still by reducing a larger, using a larger capacitor, okay? Which gives us smooth DC. Okay. The negative part of the AC waveform, which would normally be down here, is inverted. So this would have been your negative part of the AC waveform down here, but because it's been rectified, it's inverted. Okay. So although increasing the number of segments on the commutator gives us an improved DC output, it still needs to be smooth enough. So we'll still use capacitors. Okay, it allows us then to create motors within a specified size and with specified numbers of segments. go back and get this in line. Okay, just making sure that it's all in frame now. Okay, I think that's about it for now. Yep. Now again, remember U represents voltage max. Okay. Rather than Vmax, U is now universal voltage. Okay. Okay. Now here, I'm not going to read this to you. You can read it for yourselves. Okay. Right. Motors. In a motor, the current is applied to the armature via brushes, etc., etc. Blah blah blah. You can read that for yourselves. Okay. Your big boys and girls now. Okay. Lap and wave wound armature. Okay. The lap wound armature. The ends of the coil are taken to the segments next to each other. This means that there are as many parts through the armature between the positive and negative brushes as there are poles in the machine. Now, lap wound machines have an advantage when large currents are needed for larger loads. With a wave wound armature, there are only two parts for the coils between the positive and negative brushes. This type of winding carries less current than the lap wound machine, but it is capable of working at higher voltages. Okay. And here's your formula for the calculation of what lap wound in respect and wave wound. Okay. I'm hoping that will come up on the screen. Okay. Let's go back. Okay. Okay. And here we are. This here now showing you the lap wound armature windings, okay? And you can see this is your diagram in regards of your commutator, okay? It has 1, 2, 3, 4, 5, 6 segments in this case. Okay. And please note, this is the equivalent circuit of what's happening here. Okay, just flatten out on paper. Okay, so bear that in mind. Now, wave and lap wound connections and paths. Sorry, and paths. In the lap wound armature, the coils are wound and have their ends connected to form a series of parallel circuits between the brushes. Okay. So here, connecting series, and so you can almost say this kind of series parallel network, okay, in your lap wound, okay. In the wave wound armature, this then becomes just a single parallel network. Okay, the coils are wound and form only two parallel paths between the positive and negative brushes. And here you are. Even though you have these brushes here, these coils here, you only have 2 points of contact for all these coils. Whereas here you have various points of contact making with each coil in turn. Okay. Okay. So let me let's get that in view. Okay. And let me get that in view also. Okay. Let's go down a little bit, make sure we get it fully in. Okay. Let's go across. Okay. Get that in up as well. Sorry about that. Okay, let's get this you up and make sure that we can get you into frame. Okay, go back and get in the frame. Okay, right, that should be you. Now again, in the just recap, in the wavebound armature, the coils are wound and form only two parallel paths between the positive and negative brushes. Okay, in your lap wound, they're more they're connected in series parallel network in the lap wound. Okay, so what you would have here is that this resistor here, sorry, that coil would, you can almost say that the same current would be flowing in here, and in here at a given point in time. So you will need to look at this as a series parallel network without doubt. Okay, and again, you've got the formula earlier. Now again, draw these out for yourselves. Okay, do some additional research. Look at the Fintelpools books that you have at level 3, well, level 2 and 3. Okay. Okay, thank you. I hope you found this useful. Have a good day. Bye bye for now. Thank you.